Hello. As we wrap up Unit 2, a lot of the things that we focused on was determining when things are proportional versus not proportional. And proportional basically meaning that you can easily predict a future event, or you can find the unit rate or the cost per item, or the number of calories burned per mile, stuff like that. So one of the things that we looked at was equations, and I'm going to try and go through this kind of quickly, but to where it still makes sense. So equations come in two forms, and we have y equals k times x and y equals k times x plus a. This y equals k times x is what we call a proportional equation because it's always going to be consistent. The k value is the constant of proportionality, and when you have that, you can easily determine what the rate is or the cost per item, so on and so forth. And these graphs, which we'll talk about in a few minutes, are the ones that start always at 0. So they start down here at 0, 0. In the equation y equals kx plus a, this plus a changes the graph to where it does not start down here at 0, 0. So it's a non-proportional relationship. And we'll look at other types of lines and graphs later, but I wanted to kind of clarify that. So a proportional relationship, or a proportional equation, rather, is always going to be in the form y equals k times x. So we've got a couple other examples. We have this y equals 4 times x, and that would be a proportional relationship where the k value is 4. We have this example here, y equals 2x plus 3. This is a non-proportional relationship because it contains this plus 3 on the end. And we don't want that plus 3 there. That makes it not proportional. Some more proportional equations are d equals t2 times t. So even though the letters are not y and x, it's still in that format y equals k times x. Similarly, y equals 3/4 x. So in this case, k is a fraction, which is totally okay. It does not have to be a whole number. It can be a rational number. And one more non-example, y equals 0.75x plus 5. So this is a non-proportional equation because it gives us that plus 5 at the end. But k can be a decimal, which is all right as well. So those are equations. Next we have graphs. Move this line in. So what graphs look like when they're proportional. And there's a couple things that we need to remember. So a proportional graph is linear, which means it forms a straight line. It passes through the origin. So those two things need to happen for a graph to be proportional, which means the opposite is true for a graph to be non-proportional. So that would be non-linear, so it does not make a straight line, and it does not pass through the origin. So it means it does not go through 0, 0. So here's an example. We can see a couple things here, that this is going through 0, 0, and it is a straight line. So this is going to be put in the proportional category. It starts at 0, 0, and it's a straight line. Then we have an example like this. This is non-proportional because if I were to try and draw a line through this, it would be somewhat straight if I had to average them out, but it is not going through 0, 0. So if I had to try and make it fit, it wouldn't work. It wouldn't match the points that are on there. So we'll keep that one non-proportional. Then we have this graph, and it hits our two criteria. It is through the origin, and it's a straight line. This time it just happens to be, kind of like losing money or something, and kind of going negative. Here we have another example. If we were to connect all of these dots, that would be a straight line, and they would go right through the origin. So that is a proportional graph. And one final non-example. All of these points here are scattered all over the place. So you might be able to connect like these two and make it fit through the origin right there, but then you're missing all of these other points. So it would be non-proportional. And next we have tables. So tables are where you have to do a little bit more math. And for a table to be proportional, you want to make sure, where's my info? That the table has the same K value throughout. And the formula for K is K equals Y divided by X. So you may have to plug in some numbers and do some calculating to determine whether these tables are proportional. So that means that a non-proportional table gets different K values. So as soon as you have one value that's different, it is a non-proportional table. Sometimes you don't have to do all of the math. You can get away with doing just a little bit of it, or kind of, making sense of some things. And if you have the same pattern for X throughout all of the X's, and then the same pattern throughout all of the Y's, then you could say that your table is proportional as well. So a non-proportional table doesn't have a set pattern, or it may only have a pattern on the X and not on the Y, but you would need a pattern on both of them. So we have this table here, 1 and 1, 4 and 2, 9 and 3, 16 and 4, 25 and 5. So if I were to find K for each of these, that would be 1 divided by 1, 2 divided by 4, 3 divided by 9, 4 divided by 16, 5 divided by 25. Now, there's a relationship between each of these top and bottoms, but they don't all simplify to the same thing. And that automatically tells me that this is a non-proportional table. Because we have this one equals 1 whole, 1 over 1, but then right away we have 2 divided by 4, which gives us 1/2. So since these have different K values, this is going to be a non-proportional table. So we're gonna put this guy over here on that list. Oh, do we have 2 of them? So he's gonna hang out over there. Then we've got this table. So if we were to do our calculating, we've got 5.5 divided by 2, 11 divided by 4, 16.5 divided by 6, 22 divided by 8, and 27.5 divided by 10. So I could real quick plug these into the calculator and get an answer. So 5.5 divided by 2 is 2.75. 11 divided by 4 is 2.75. 16 16.5 divided by 6 is also 2.75. 22 divided by 8, 2.75. And since we have that last value in the table, we do get 2.75 as well. So since we have the same K value for each of these, this table gets to go to the left side. It is proportional. We'll make this one a little smaller. All right. Here's one that has a pattern. I like patterns. Patterns make it really easy and really simple to do this. So every x is going up by 1. Well, not that. So there's a pattern there. So we have a pattern for the x's. And every y is going up by 12 each time. So there's a pattern for the y's. Now the 1 and the 12 don't have to be the same number, but you have to have the same pattern all the way through the x's and then the same pattern all the way through the y's. So this one does fit. It is proportional. So it comes over here. Make it a little bit smaller. We've got a couple more to look at. Let's see. Do we have a pattern? I think we do. So -2 to 1 was +3. 1 to 4 is +3. 4 to 7 is +3. 7 to 11 is +4. Well, we can check it. So we've got a pattern for the y's. This is +12. Then we've got another +12, +12, and then 23 to 39 is actually +16. So we have these guys that all have the same pattern, but then we've got 4 and 16. Now, I can't rule that out yet because I could find the same K value for all of these. So, pulling out the calculator, real quick, we're going to do 13 divided by 2, and we get, let's use a different color, 6.5. But then 1 divided by 1 is 1. 11 divided by 4, 2.75, that's a 2. 23 divided by 7, that's a 3 something, and then 39 divided by 11, I don't think it matters what we get because it's going to be way off, 3.5. So this was no pattern and different K values. So this table is going to get kicked over to the non-proportional side. He's going to be over there. So the biggest things are to make sure that you've got the same K value throughout the whole table, or you have a pattern that's consistent for y's and x's.